Hi everyone, and thanks for joining us today for our webinar, A Deeper Dive into SAR, Agriculture, and Land Surface Deformation. We have over 1,300 people signed up for this webinar from around the world, so that shows the interest that people have in the SAR industry. So thanks for taking the time to join us. Before we get started, we have a few housekeeping items to go over. First things first, everyone on the phone line is muted. So if you have questions, use the questions box to go through oh, sorry, there was a little bit of a lag. Use the questions box to ask any questions. We will have time at the end to go through that. Additionally, if we do not get to your question, someone will follow up with you. Speaking about time, this webinar we'll have about 45-50 minutes of content. So we'll take up most of the hour. We will send you the webinar is being recorded. You will get a link to the webinar. You can check out our website at www.harrisgeospatial.com for that to be posted in the next couple of days as well. You will also get a survey. We would love to get any feedback you have about the webinar, just so we can make sure everybody has a good experience. So let's introduce our speaker for today. If you've been watching our two previous webinars, then her name will sound familiar, Megan Gallagher. Megan has a master's degree in geophysics with a focus in satellite remote sensing. So welcome, Megan.
Thank you, Zach.
In addition to that, Megan also has a bachelor's degree from Colorado School of Mines, the same place that I went to school as well. Before we turn things over, we have a few other slides that I'm going to walk through just to give a quick introduction for Harris Geospatial Solutions and what we do if you're not familiar. So first, here's a high-level overview of our kind of software/solutions portfolio. MV and SARscape are two of our core products and technology, commercial software packages, which those are the pieces of software that are actually used to create the results that Megan is going to be sharing today. Whole bunch of other little items here, many other vertical markets or industries that we work in apart from what's listed. But since we're focusing on MV and SARscape, let's take a closer look at those tools. First, MV is a desktop application for sitting down, going through workflows, and that's what these couple little dialogues here represent, some SAR processing workflows. Down in the bottom right, you'll see little pink boxes, yellow boxes with lines connecting them. That's a screenshot of the MV modeler where you can actually automate all of this SAR processing. So if you're a SAR expert, you're a scientist, you understand what parameters need to be set to, you can create that workflow, share that with a coworker who can then go through and process data, extract the information they need. In addition to this, if you are an Esri user, whether it's ArcGIS Pro or ArcMap, all of our tools and technologies integrate seamlessly within the Esri interface. So if you are an Esri user, you can run SAR processing, you could create workflows in the MV modeler or ArcGIS's model building tools as well to automate your workflows. Lastly, all of this stuff can also be exposed through a web interface on enterprise with headless or batch processing. So this is just a quick little screenshot showing the result from SAR processing. In a browser, you'll see the outline of the image with a little web-based map behind the scenes. And two more slides before we turn things over to Megan. First, if you haven't gotten enough information from SAR about SAR from these past couple webinars, we do have an upcoming SAR training class in Broomfield, Colorado. So visit our website. You can sign up for that today. It's 4 days long. So that's if you want to get hands-on experience with the software, learn a little bit more about how to go through process SAR and be able to talk technical talk all you want with people who are well-versed in SAR technology. And just one other thing to note with that, we do have other classes around the world, so you can see a little SARscape training schedule here. And in addition to this, if you want to go through and attend the training classes, you get your hands on MV and MV SARscape training classes will be included in the SARscape Fast Start. If that's something that you're interested in, you can reach out to us and we'll get you in contact with the people you need to talk to. And with that, we'll get the boring stuff out of the way and turn it over to Megan.
All right, thanks, Zach. All right, so for a quick overview of what we're going to be covering today. First, we're going to start with agriculture monitoring. We're going to go over some background details that are really important, then look at some time series analysis and classification. After that, we're going to go to the land surface deformation part of this webinar. Once again, we're going to start with some background and then do an example case with small baseline subsets. And if there's time at the end, we'll hopefully be able to answer some questions. The first topic that we're going to cover today is using synthetic aperture radar for agriculture monitoring. There are many benefits when using SAR for this case. The first and foremost being agriculture is grown in areas where there is frequent rain and cloud cover, making standard monitoring with optical imagery, even UAVs and UASs, prone to miss large periods of time, which may be essential for understanding things such as plant health, growth, and biomass. Another benefit is that with the different bands and polarizations, we're able to gather unique information about crops that can be used to get different characteristics than optical imagery. So first, we're going to go over some of that need-to-know information when you're using SAR, and then we'll go straight into some uses. Here's a comparison between an optical and a SAR image. The optical image is a Sentinel-2 scene from June 20th, 2018. We can clearly see the areas of green vegetation and barren fields from this picture. With analysis such as using spectral indices and time series analysis, we're able to find out possible crop types and track growth and change over time. On the right is an Airbus TerraSARx VV image from June 18th, 2018. And looking between the two, we notice some differences. Look at the red circle for one example. Even though all these areas show up on the green gradient or barren in the optical imagery, we have a large difference in backscatter in the SAR, which we will be going into in much more detail very soon. As a quick overview, the backscatter of SAR is affected greatly by crop type, soil moisture, and geometric effects, thus making certain vegetation appear very different from similar green-colored vegetation around it. Areas that are very bright white have a high intensity response. Think of it as the more the vegetation, the denser, the larger the leaves, and some other factors, the more the intensity is going to be scattered back to the satellite. On the opposite side, if it is bare, flat soil or wet soil, it will act similar to other flat surfaces and reflect most of the backscatter away, appearing black in our imagery. For a quick refresher, radar bands are the frequency of the signal that is emitted from the instrument. The most commonly used band frequencies are highlighted here in red. Band frequency is directly related to what is seen by the SAR sensor. So, for example, longer wavelengths or lower frequency SAR signals penetrate deeper into material such as vegetation and soil. In addition to penetration depth, the band frequency will also determine the size of features that your SAR data is sensitive to. Waves interact with features that are similar in size, so high-frequency X or K-band SAR has a very small wavelength and essentially sees materials of similar scale, such as leaves on trees. Usually, L and P band pierce through the vegetation and will return with information on the soil. This is used commonly to understand soil moisture effects. X and C, on the other hand, scatter off of the canopy and return information on the plants themselves. We will be using X and C band examples in this webinar using TerraSARx and Sentinel-1 data. As such, we'll be gaining information off of the canopy and the volumetric scattering that occurs as the plants grow over time. Some other useful information is how these bands tend to react to different crop types. X-band is useful for detecting vegetation with broadleaves, such as corn and soybeans, and also joins C-band in giving optimal information on grains. There is a marked difference between grain crops such as rice, soy, or barley, as they're much easier to see and track with publicly available SAR than subterranean or near-surface crops such as potatoes. The last important thing to note about the band effects is the shape of the crops themselves. Different growth stages can be seen in the backscatter, and with high enough resolution SAR, differences from plant to plant can be marked. Next, another quick refresher, this time on polarization. Polarization is the direction of the wave that is projected from the radar, and then the direction of the wave that is returned after it has bounced off of an object. By that, we mean if a wave leaves the satellite and is oscillating up and down or vertically, then hits an object on the ground and returns with the beam oscillating vertically again, you have a VV or vertical-vertical polarization. When the polarization is VV or HH, it is called copolarized, and when it is VH or HV, it is cross-polarized. Different polarizations react differently to ground surface characteristics. So the more polarizations that you have, the more in-depth an analysis you can go. Polarization plays a large part on the information that is returned from SAR backscatters over agriculture. So depending on what information you need, it is important that you choose the right polarizations to start with. To get optimal information on vegetation, you're going to want quad polarized SAR. This means you have all four bands, VV, HH, VH, and HV. However, sometimes this isn't possible, in which case dual polarization, so VV and VH or HH and HV, can still inform on many different agricultural aspects. Each polarization is usually affected by different aspects of the soil and vegetation interactions. So here's a quick general overview with what every polarization is best at. HH tends to get a large response from the soil itself, so is useful if you want to get more information on what is happening underneath the crops or want to monitor soil moisture. VH and HV are sensitive to volumetric scattering from the canopy of the vegetation, so we'll pick up changes from when the crops begin to sprout and grow leaves. VV backscatter is affected greatly by the vegetation structure, such as the stem, branches, leaves, and flowers of the crops of interest. However, if the vegetation is dense enough, VV and VH will have the same responses, as they will be unable to pierce through the canopy layer. The imaging graph on the right show how Sentinel-1 VV and VH react over different vegetation. VH is always lower than VV, and VV tends to be more sensitive to crops than VH. VV is shown to pick up large signals over the bright field areas, but also shows variation over the dark fields, where it is picking up scattering from the soil or from early plant growth. The next factor that we're going to talk about is geometric effects on the ground and how they affect the backscatter. We've talked previously about effects such as shadowing and layover that are caused by the angle of the satellite versus the angle and topography of features of interest. On a much smaller scale, other geometric effects will change our backscatter response in direct relation to vegetation itself. Things such as direction of rows or the patterns of planting affect the response that we're going to get from our SAR sensors. This means that you might be looking at two fields of the exact same plant that are going through growth stages at the same time, but because one has horizontal rows and one has vertical rows, the responses might look different in between the two. Besides vegetation itself, rough soil, such as recently plowed, will also have a different reaction than flat soil. So it is really necessary to have in situ data when you're doing SAR monitoring over agriculture. This will help greatly in understanding specific SAR backscatter responses, as well as give you much more detailed information that you'll be able to use throughout your studies. Weather also affects our SAR scenes. And no, not just random snow or hailstorms when they really shouldn't be there, but normal seasonal effects. SAR can see through clouds and rain, though the rain may cause some noise, but the moisture from the rain will gather on crop surfaces and soil, changing how they look in the SAR imagery. This can be leveraged to get relative moisture contents. You will not be able to get absolute moisture content, but by doing time series analysis, you can track changes and be able to analyze how the moisture is changing in your area of interest. Wind will move the crops so they appear differently than they may have on other dates, possibly confusing your analysis. So it is always good to take a look at what the weather was like when you're getting your imagery. The area we're going to be viewing today for our examples is near Troyes, France. This area is rich in agricultural diversity, with multiple crops from grains, flowers, grass, vineyards, and near-surface crops such as beets. Monitoring done on these crops faces many of the same problems it faces globally. The area is mostly cloudy during the winter seasons, which might cause issues for monitoring things such as winter wheat, and is partly cloudy for most of the spring and summer growing seasons. With the temporal period of publicly available optical imagery, even areas that are partly cloudy may cause the loss of months of data that could help with understanding of agricultural growth. We will be using 3 different systems for these examples. TerraSARx data from Airbus from May to October 2018, Sentinel-1 C-band from Copernicus from October 2017 to November 2018, and Sentinel-2 optical imagery over the same time period as the TerraSARx. On the screen, you're seeing 4 Sentinel-2 images over a field highlighted in red. Over this 3-month period, these are the only usable Sentinel-2 images. And you can see the large gap in between the barren field in June and the beginning of growth on August 4th, the greening in late August, and suddenly an empty field in the end of September. We are missing a lot of crucial information about the growth cycle with the limited access of this optical data. So let's see what SAR can give us. All of our SAR datasets were run through the tool Intensity Time Series workflow. This workflow goes through all of the pre-processing steps that we have gone over in the previous webinars. Multi-looking is used to remove noise by averaging over pixels in our areas. By averaging over pixels, this does reduce the resolution, but also reduces the speckle that occurs. Co-registration, there we go, is used to map every scene to the other to make sure they're all over the exact same coverage, which is necessary for the next step. De Grande spatial temporal filtering uses at least 3 SAR scenes to filter out more noise over time, using all of the scenes for information. We've previously spoken about other filtering options. And when you're working with a lot of scenes over time, this is the best filtering technique to use. Geocoding and radiometric calibration are used to reproject from satellite line of sight to map projections, and then calibrate the data so it is comparable from scene to scene and with other data. Then this process has an extra automatic step that picks out important multi-temporal features, making it easy to understand the changes that are occurring. You can choose which features you want output or just go with the default information. Let's take a look at what we can get. The first output that you get is an image where every band is a different date of the SAR imagery. It automatically orders them from earliest to latest image, so you don't need to worry about moving things around. The image on the left is made of 3 different dates, shown as the red, green, and blue bands. This allows us to easily view changes within our scene and pinpoint how certain fields are acting during what time periods. A secondary output from the automatic time series processing is also all of the statistics of the areas that we chose in that last processing step. This includes minimum, maximum, mean, covariance, etc. The image on the right shows a covariance minimum gradient image as the bands, and shows great differentiation between urban, forested, and agricultural areas. This can be used then to easily segregate and classify our areas of interest, and gives important insight into the fields themselves. Now let's look back on that field we viewed with our 4 scenes of optical data with all of the different SAR sensors. At the beginning of this time series, we see high intensity responses. This is due to plowing and churning of the soil that occurs, as you may have noticed in that June optical image. This can also be caused if fields rotate different crops during the seasons. In the beginning of July, we see a minimum, which is highlighted by that green line. The minimum is related to the sowing stage of this serial field. After that, the response slowly increases as vegetation grows and the intensity of our backscatter off the canopy and structure increases. In mid-September, we hit a peak in the Sentinel-1 data. This is caused by the harvesting and upchurning of the soil, as well as the leaving of some of the vegetation detritus on the field. Soon after, with the red line, we see this decrease in TerraSARx, which occurs when harvesting is finished and the soil has returned to a more normal state. An important thing to note is that X-band is more sensitive to backscatter over C, and so can even anticipate variation that is occurring on the soil surface. If you had an X-band and a C-band satellite going over a field at the same time, the X-band would be able to let you know first about the different stages of growth that were occurring. Moving on from just one field, let's take a look at the temporal separability of multiple crops. Similarly to optical, we can use the images made of dates to track the changes over the entire fields and compare them for analysis. We have found 3 fields of interest, and using the time series viewer tool, we can make a comparison of their growth rates over time. Changes in the intensity shows how these fields differ and can be used in tandem with optical data to get an understanding of SAR optical crop interactions. With this, you can track temporal changes from crop to crop, field to field, or even over an entire scene to see how these crops are growing and how they compare to each other. Another output that you get from the intensity time series workflow is statistical information on the fields related to the dates themselves. On the screen, we are viewing a few of these outputs. The maximum date output on the upper left-hand corner shows when areas had the highest intensity response, usually having to do with maximum plant growth or when the farmers are working on the field. The minimum date is related to the sowing stage in agriculture for most grain crops, such as barley. The max ratio and max increment both give information that pertain to specific crop stages. So once again, for example, with grains, the maximum increment picks out the emergent stage when plants begin to grow leaves, making it easy to track fields versus fields for growth and management purposes. So with date outputs, we can get an understanding of the growing period of the agriculture and also create shapefiles and use it for classification purposes. So speaking of classification, because of the unique time series and statistics, we can pull out our classifications of specific field types. For example, on the screen, we use training data over the time series, shown on the left, to find all of the wheat fields, shown on the right. There is a little bit of confusion with some of the other crop responses, but overall this quick classification did a great job of finding all of the other wheat fields, and then can be used to create shapefiles and track their temporal changes for comparison. Lastly, I thought I might show that SAR imagery works with other agricultural analysis tools as well. In this example, I ran the ENVI Crop Science Developing Hotspots tool over a small group of fields. This tool compares two scenes to see how the vegetation is growing compared to the surrounding vegetation over time. Green means growth, and red means harvesting or decrease in this example. We can track the changes over time as the fields begin to sprout, grow, and then are harvested. This tool can also be used to compare within a field itself to see if there are any areas that are more or less healthy than the surroundings, to pinpoint possible diseases or optimal planting practices. And there we have a quick overview of just a few things that are possible when you're using SAR for monitoring agriculture. Now, there are many more options, such as tracking soil moisture changes, ascertaining plant biomass, and getting detailed crop information with high-resolution SAR. Data fusion between SAR and optical can also be used to great effect, where you can use optical information when it is available to inform with normal methods such as spectral indices, and then use the SAR data with its temporal normality to inform you when the optical is unable to do so. And now we're going to move on to the next topic. Land surface deformation. So when most people think of SAR data, in general terms, this is what they think of, and for a very good reason. If you watched the previous webinar, we brought up an interferometric example, where we compared two scenes during the Hawaiian eruption to view movement that was occurring. Today, we're going to go far beyond that, but use the same principles to do a long-term time series analysis of fine-scale movements. This kind of analysis is exceptionally useful for monitoring of priority areas, such as dams, fault lines, mining and construction areas, or areas prone to land surface creep. So before we go in, we're going to do a quick background on phase and interferometry. The images on the left show the phase response of two SAR scenes, which don't make any sense to us at all and honestly look a lot like static. However, if we look at the phase change that is occurring between the two scenes, which is that interferogram in the middle, we can gather information that can be used to look at topography or displacement. The diagrams on the right show how we get either of those. The one on top shows topography, where you have a view from the satellite at a slightly different angle. The orthogonal distance in between them is called the normal baseline. The larger the baseline is, the more precise DEM you can get. The one at the bottom shows an example of displacement. Instead of having a normal baseline for distance, you want to have a view over the same area at different times, or a temporal baseline. If you have a very large normal baseline, you will not get high-resolution displacement products. Sentinel-1, for example, is made for creating displacement products, as it has a very small normal baseline and high temporal repeatability, thus why you never want to use it to create a DEM. Here's an example of what having a large normal baseline does when you create a DEM. The interferogram on the right has twice the normal baseline of the interferogram on the left, greatly increasing the amount of topography that we're picking up and will be able to use in our analysis. You could almost think of those fringes as contour lines. So with the larger the normal baseline, the more details we're getting on the topography. Of course, the more details we get, the more complicated the processes that we'll have to do to actually figure out what's happening on the ground surface. Now, you may have noticed I did sneak in an equation, which is really important for the understanding of why we need time series analysis for our high accuracy monitoring. With only a pair of scenes, you have to make a choice between creating a DEM or a displacement map. This is because you just don't have enough information to get both. For a DEM, we assume the surface is not moving, and for displacement, we assume it is. When we start using more than one pair, we can gather more and more information to fill in those gaps, such as getting rid of atmospheric effects and other noise sources, though the noise will always exist as it is part of the backscatter signal. So when do you need just one interferogram, and when do you need to do time series analysis? It depends on the magnitude of the event you're trying to track. On the left, we have an interferogram generated over an earthquake, and we can see the general movement easily over this area with the concentric rings because the event was so large, it engulfed the noise and atmospheric effects. On the right, we have an interferogram that you don't see those patterns in, because whatever movement is occurring, it is so small in between those pairs that it is overwhelmed by atmospheric effects. That's when you need a time series process. So for a bit of background, if you haven't really looked at an interferogram before, the cycles that we saw relate to displacement. On the screen, we used one master image and then compared it to other scenes that occurred 11, 22, 33, 44, 55, and 66 days later. What this shows is the change over time in the movement of the area. Every color cycle, which one example is shown on the far right image with that red line going from that pink magenta color to the other outlying pink magenta color, has a displacement of about 1.5 centimeters. So we can track these changes over long time periods to understand the surface displacement. This is also a great way to check for noise in a scene. By tracking this one area, we can see consistent changes that are occurring over time, so we know that it's not caused by atmospheric or topographic effects. Now, in general, there are two kinds of long-term displacement monitoring techniques: SBAS, or small baseline subsets, and PS, which is persistent scatterers, both of which are available in SARscape. SBAS works with non-linear behavior and works in urban and non-urban areas, and as you can see from the image on the left, also seems to smooth out change over the region. Persistent scatterers is used for linear behavior over objects with consistent signals, such as urban regions and rock outcrops. It can have a large difference between adjacent pixels. It will also ignore large areas that lack coherence instead of trying to interpret them. So as you can see in the right image, there's a lot of areas that are black, and that's water. Today, we're going to be going through an SBAS example. A short overview of the entire process is we take a stack of SAR scenes that are the same geometry, path, row, and polarization, and we find out how well they are related to each other over time and space. And then we can go through some processing to create fine detailed displacement and topography maps. Our area of interest for the SBAS processing is the Mumbai Airport in Mumbai, India. This study was done by SARmap and was finished in August of 2018. For this study, 54 Sentinel-1 scenes were used with a descending geometry, as this is the only one available over this region. The time period was set for September 2016 to July 2018. The revisiting period of the satellite over this region is every 12 days. VV polarization is used as you only want to use co-polarized data when creating interferograms. Let's take a quick look at our area up close. On the left, we have the intensity image of the SAR scene. Bright white are urban areas, the more grayscale are usually rural or dirt and vegetation, and the black is mainly water, except for one area in particular. On the right, we have an optical image of the airport to get a view of our area of interest. There are multiple runways through the airport with nearby surrounding areas of grass and dirt, which are then directly surrounded by urban development. And now we can zoom in and see the airport clearly with SAR. Because the runways are so smooth, they reflect most of the backscatter, similarly to how water would, making them look black. The areas of grass and dirt that surround the runway are that gray color, and the surrounding buildings are that bright white response. Now let's take a quick look at those processing steps. So SBAS is a very complicated process. And if I was to cover it all in detail, we would be here for a few hours longer than this webinar is supposed to be. So I'm going to go over the steps at a high level, but I'm going to point out tips and tricks for when you do this process. This process is semi-automated in SARscape as well, so this overview should allow you to try it out on your own. The steps we're going to go through are creating connection graphs, generating interferograms, refining those interferograms, and then going through 2 inversions to clean up the data. And lastly, we're going to geocode it so it is in proper map projections. On to the first step. The connection graph step is used to find the relations between all of the scenes that are going to be used to create interferograms. For this example, the most important things to note are the 2 parameters outlined in red. Those parameters set boundaries for what we're actually going to use out of all of the scenes downloaded. If there's a long time period in between 2 scenes, or too large of a normal baseline, we will lose coherence and be unable to create good interferograms, thus causing unnecessary noise. And here's the connection graph that was generated for this example. This is what a good connection graph looks like. First, we see 2 red dots that are separated from the rest of the graph. These dates fell too far away from our maximum temporal baseline, and so are not being used in this process as they will add noise to it. The rest of the graph shows high interconnectivity between the scenes. In general terms, it is good to have 5 connections between every point in the scene to build up the amount of information needed. Every single line that exists is going to become an interferogram between a pair of images. You may be able to see that 1 dot in the middle is bright yellow. This is the scene that has been chosen as the supermaster. This is the scene that all other scenes will be co-registered to and will be the reference image. This is chosen automatically in the tool, but you can choose it for yourself if you want to. Here's a view on why we set that temporal baseline maximum. Temporal decorrelation occurs between scenes when there are large changes over time, things like construction or vegetation growth or even just seasonal vegetation changes can cause this decorrelation to appear. The interferogram on the left used a pair with 12 days in between, and the bottom picture shows the coherence between the pair, which is high as seen with that bright white color. The second pair has 120 days in between the scenes. We have a large area of low coherence seen in the black on that grayscale coherence image, which leads to that strange noisy effect in the interferogram above. After the connection graph has been generated, you can now move on to creating the interferograms between every pair. Some tips for this process are you usually want to use the Delaunay MCF as your unwrapping method type, and the absolute lowest you should set your coherence threshold to is 0.2. The coherence threshold is the filter for how low of coherence you're allowing areas of the scene to have, and it is a range between 0 to 1 with low coherence at 0. Because of the amount of interferograms that are going to be generated using this method, we can set this to lower values than usual. However, this is a careful balance. If you set the threshold too low, you're forcing the program to accept areas that may cause noise further down the processing line. If you make it too high, you lose spatial information as it drops those areas of low coherence. So there is a fine balance in the choice that you make. After this step, you're going to want to go back and look at the interferograms that are generated to check for artifacts that may have occurred during processing. You can then remove these interferograms from the next steps by going back and editing the connection graph. Refinement and Re-flattening uses orbital and ground control point information to work within the scenes to make them more precise. The ground control points can be made in the exact same way as in Webinar 2 for the displacement map, and can be made as part of the process within the SBAS workflow. But there's one very important thing to note. GCPs for this process are necessary for finding movement. When you create a GCP, you're saying that the area is stable and that all movement in the scenes is relative to what you have stated stays the same. So if you choose areas that are moving as your GCPs, other areas that are actually moving may look like they're staying still. Also, because you're working with a large time period of data, you need enough GCPs to be in every scene. So you may need more than 30 to get accurate results through every single interferogram. The first inversion calculates residual effects from the interferograms and reflattens them to get rid of noise. It is the first step that gives an estimate of displacement and topography. This is also the step in which you can choose the type of displacement that is occurring in the scene, from linear, quadratic, or cubic models. Most of the time, linear is going to do a great job of tracking movement. So things like long-term surface movements, like slow-moving landslides, being one example. But in certain situations, quadratic or cubic may fit the changes that are occurring better, such as if the area was stable for a long time period and then a sudden movement began to occur. Linear might not be the best fit. It is best practices to run first with linear and then check your results. If your movement looks to be more cubic or quadratic, you can run it again with the proper model. This is also the stage where you can actually check if those areas that you said were stable with your GCPs are actually stable. And with that information, you can go back and move them around if necessary. The second inversion is the final SBAS processing step to fit all of our scenes to the chosen velocity model. This step also removes the atmospheric effects in all of our scenes. And because I've brought up that term a bunch of times, let's take a look at what it actually looks like. So, atmospheric effects are caused by small changes in the atmosphere that overwhelm the phase change response. With a pair of images, it is difficult to get rid of this effect, and there are algorithms, but they aren't precise. With a stack of images, we can remove the atmospheric effects and finally be able to view just the ground surface movements. The last step in this process, I hope looks a bit familiar by now, is to geocode all of our imagery, so that it is no longer in the slant line view of the satellite and now is in normal map projections. With the images we're about to see, I do need to go over one more topic. When you're using one acquisition geometry, in this case descending, you do not get true displacement, but rather line of sight, or LOS displacement. This means that the displacement we view is relative to what the satellite angle is. So in the upcoming images, red means the displacement is towards the sensor, while blue means it is away. It is also important to know that line of sight displacement is less than true displacement, as it is only a fraction of the total movement. And here is our displacement velocity map. On the right, we see some large areas of blue and purple, which mean movement was occurring in the scene over those regions away from the satellite line of sight. Those areas of movement are occurring near the runways on non-paved surfaces. On the western side of the image, we can see movement wrapping around the runway, and on the eastern side, we see large areas in between two runways that has been moving. We can also see some areas of purple further out in the city, but the airport is mainly surrounded by green, light blue, and light yellow, meaning very little movement has occurred. And let's get a close-up view on one of those areas of movement. We're taking a look at that purple area right in between the runways. This area is averaging about 8 millimeters of movement a year. And here's the most powerful part of this tool set, which is tracking the movement over the time scale it occurred in. Instead of just getting an output that says that movement has occurred, we now have a catalog of what movement and when the greatest period happened. With outside resources, this can be correlated to other effects such as rainfall or construction. The plot on the bottom right-hand corner shows the change over the 2 years, which is generally decreasing about 2 centimeters, but then we see an uptick in the end of 2018. A second example is of the eastern runway movement, with about 1.5 centimeters of change occurring over this time period. So, in total, SBAS is a powerful tool that allows for us to view fine-scale displacements and to understand when they're actually happening. This technique is great for monitoring areas of interest and can even pick out subsurface movements such as the development of sinkholes. It can be run once with all of your data and then updated to run with new scenes as they come out for monitoring efforts. An interesting thing to note is that 2 months after SARmap completed this study, the Mumbai airport closed for 6 hours for reconstruction work on the runways. And then it closed again in February of 2019 for further reconstruction. And with that, I'm going to pass it back to Zach.
Thanks, Megan. Hopefully everyone agrees she's been a rock SAR. Nice little pun there with her presentation. Just a quick couple of slides before we get to questions and discussions. First things first, if you still want to learn more about SAR, in addition to our training classes, there's also a SAR Analytics Symposium that will be coming up in Rome, Italy later this year in October. So this will be similar to the MB Analytics Symposium where space will be limited. I think there's going to be about 120 seats. So if you want to go, sign up now. I think they've got calls for speakers, abstracts as well. So great event, especially if you're in Europe, you can attend, it's local, or it could be a good excuse for you to go on vacation if you're in the Americas. And with that, I'd like to say thanks, Megan, for presenting, and we will go through and answer a few questions now.
Grab us the questions.
Looks like we got a good number of them. Go ahead and pick one out for you. Can you extract soil moisture content from SAR data?
So you can extract general soil moisture content. So it's sort of relative. You won't be able to get absolute soil moisture, but by tracking changes over time, such as having a dry scene and a wet scene, you'll be able to see the change in the SAR scattering. So for having moisture on crops, it actually scatters more than it would normally. If you have moisture on the soil, it scatters less because it gives it more of a flat effect. So you can track these changes, and if you have in situ data as well, you can track that soil moisture change that is occurring.
All right, thanks, Megan. Here's a question which I can actually answer. Can you elaborate on how you developed the Hotspots map that you showed in the agriculture section?
Oh, yeah.
I can do that one. So that is with the hotspot analysis tool, developing hotspot analysis tool in MD. And so what that's going to do is between two images, so in this case it's with SAR amplitude. So it's going to look at the areas and look at the statistics for your region and identify the places that are statistically significant where the amplitude is changing from time 1 to time 2, or where the amplitude is decreasing from time 1 to time 2. So as Megan has described, that the change in amplitude could come from a handful of different things, whether that's the crops growing more, getting more leaves, or maybe being harvested. So we'll see that the difference in backscatter getting to the sensor. There's a question for Megan. Are there any benefits from fusing optical and SAR data?
Yes. That's your answer. The answer is yes, absolutely. So the thing is commonly optical data is usually used in the Americas when we're looking at agricultural growth. It's just sort of a standard. And so we have a lot of analysis using spectral indices and different tools to get an understanding of what's happening at the crop level. However, like I said in the beginning of this webinar, clouds and rain can cause a lot of problems with this analysis. So when you're able to use these techniques that we used for a very long time and understand well, and then add in SAR, which gives us even more information on physical characteristics, you're going to not only get higher classification accuracies, but even more understanding of what's actually happening in the scene. And if it's a really rainy year, you will be able to see what's going on with the crops, even if optical imagery doesn't work.
All right, here's a question. I think this was probably answered in one of the earlier webinars, but a good concept to understand nonetheless. Can you talk a little bit about what coherence means between two data sets?
Yeah, so coherence is more or less the similarity. You look at both the imaginary and real parts of the images, and you see how similar they are. So those areas that were really white were very similar. So we had similar backscatter responses. And those areas that were really dark had low coherence. Things that can cause low coherence are large movements, Vegetation is pretty good at causing low coherence, such as very dense, forests and trees. And so when you're trying to find similarities between SAR scenes, you can actually use that lack or that amount of coherence to find things out, such as I've used the lack of coherence between scenes to find boundaries of fires that occurs. But when you're looking for displacement, it's good to have that high coherence so you can actually see the changes that are happening.
All right. I'm going to try to combine a couple questions together here, which are pretty similar. If we have an earthquake or volcano, how could we use SAR to extract information on the changes that occur? And what type of SAR data, I don't know if that might be related to polarization or not, would be best to extract that information?
So yeah, I'll start with the what type of SAR data. So if you're talking about bands, it depends on the characteristics that you want to pull out. L and P band usually see through more vegetation. However, there aren't that many satellites at the moment that have them. C and X band are the most well-known and used at the moment. And so those are the ones that people usually use, though there are quite a few L band in that category, excuse me. If you're talking about polarizations, when you're looking at deformation specifically, you're going to want to use copolarized, so VV or HH. And then for the second part of that question was using earthquakes and volcanoes. And so when you're looking at that kind of stuff, you're going to want to use interferometry or INSAR. You can use one of these long-term time techniques if you're tracking, like, say, the movement of a volcanic flank and trying to see how it's changing. But if you have a large effect, such as many of the different earthquakes that occur where we have centimeters to meters of movement, you can use a pair, so just two scenes from before and after, to get a general understanding of what has actually happened.
Now, here's a follow-up question for that. Okay. So if you have a lot of change when there's an earthquake, what's the largest displacement that you'd be able to detect?
So it depends on the wavelength of your satellite sensor of choice, because if there's a lot of change, you're going to lose coherence, and that'll mean you won't actually be able to see that change. Now, if you have a buildup of information before and after, you can see the difference in between them, but it actually depends on the sensor that you're using.
Thanks. So we'll answer a couple more questions, and then we'll call it a day. Here's a good one. I know Megan's explained to me before. If we have an area with a lot of vegetation, are you able to monitor surface deformation with SBAS or persistent scatter?
So that actually is once again dependent on the band and the amount of vegetation. So if you're looking at a dryland area with shrubs and grasses, you should be able to get the ground surface deformation. However, if you're looking at thickly forested areas with dense canopies, the SAR signal will not be able to get through those canopies and will instead bounce off the vegetation. So L and P band can pierce through the canopies better than X and C, so that could be an option depending on how thick of vegetation you're looking at. But you also might be able to find, just looking at a scene, areas where there might be less dense canopies and use those points to see if there's movement.
All right, here's another one. So, during the presentation you mentioned that you can get a little bit of noise when SAR goes through clouds or rain. Are there any challenges when you have extreme weather? So maybe you have a storm that's got a lot of downpour, a lot of moisture in the air. Will that affect your results?
It definitely will. So, the great thing about SAR is, yeah, you can see through clouds, you can see through rain, and these are normal effects, but it does get more scattered off of things like hail, snow, torrential downpours. Actually, previously in the webinar, right when we were going through the agenda, there was actually an image of Cyclone Idai, and you could see from that, you could actually see the tracings of the cyclone in the water. And so things such as very large weather effects will affect what you can see with the SAR and might cause a lot of noise.
All right, let's see. I don't know if there's any other ones. Maybe you see one that you might want to address. But I think with that, we'll call it a day. So if we didn't get to your question, we are going to create a FAQ that will be sent out with a follow-up email, which will include a link to this recording. You can also check our website in the next couple of days, and this will be posted there as well. So feel free to reach out to us if you have any other questions. Hope you guys enjoyed the webinar. We'll see you later.